Hello everyone, my topic today is extreme value theorem. I will talk about how this theorem moves from MA1 to MA2. In MA1, we study one variable. In MA2, we study more variables. So the main question is simple. Can we still make sure that a best value exists? First, let us recall the MA1 extreme value theorem. It says if D is non-empty, closed, and bounded in R, and if F is continuous, then F has a maximum value and a minimum value. In simple words, if the input set has no hole and no open end, and the function is continuous, then the highest value and the lowest value must be reached. This is what we already know in one variable. Now let us look at a real problem. A company wants to build a distribution center. The place must be inside a rectangle. There are three demand points, A, B, and C. Each point has a different demand weight. So the total transportation cost depend on two things, the X position and the Y position. This means the cost function is fxy. Now we want to find the best location. But before we calculate it, we need to ask one more basic question. Does the best location really exist? Here, D is a subset of R2, not R, so the MA1 theorem cannot be used directly. This brings us to the main question. Many real problems have more than one variable. For example, a function may look like this. The input is not just one number. It is a point in Rn. So we ask, can the extreme value theorem extend from R to Rn? This is the bridge from MA1 to MA2. The answer is yes. The multivariable extreme value says let D be a non-empty compact subset of Rn. If F is continuous, then F has a maximum value and a minimum value. The key word here is compact. In Rn, compact means closed and bounded. So the idea is still very similar to MA1. Closed and bounded set plus a continuous function gives maximum and minimum. Now I will explain the proof idea. We do not try to find the maximum point directly. Instead, we look at all output value of the function. Let S be the FD, so S is the set of all values that F can take. Since D is not empty, we can choose one point x0 in D, such as fx0 in S. So S is also not empty. Now the maximum value of F is just the maximum element of S. So we only need to prove two things. First, supremum S exists. Second, supremum S in S. If both are true, then S has a maximum. The proof for the minimum is similar. First, we prove that supremum S exists. We use one important theorem. A continuous image of a compact set is compact. Here, D is compact. The function f is continuous. So S is compact in R. By the Heine-Borel theorem, compact in R means closed and bounded. So S is bounded. Also, we already know S is non-empty. So S is non-empty and bounded above. The completeness axiom tells us that the supremum S exists. We call it M. So the first part is done. Next, we need to prove that the supremum is really inside S. This is the key step. For every natural number k, the number m minus 1 over k is smaller than m. Since m is least upper bound, m minus 1 over k cannot be upper bound. So there is some yk in S such that m minus 1 over k smaller than yk. Also, because m is an upper bound, we have yk smaller than m. So m minus 1 over k smaller than yk smaller than m. This means yk is getting closer and closer to m. So use this integration by the squeeze theorem. Yk approaches to m. Now we use closedness. Since S is compact, S is closed. We have a sequence yk in S, and this sequence goes to M. Because S is closed, the limit must stay in S. So M in S. Also, M in FD. So there exists some point x max in D such that f max equals to M. This means f rarely reaches its maximum value on D. So the maximum exists. The proof for the minimum is almost the same. Since S is non-empty and bounded below, the infimum exists. Let M equals to infimum S. For each k, we can choose zk in S such that m less than zk less than m plus 1 over k. Then zk approaches to m. Since S is closed, the limit m is also in S. So f also reaches its minimum value on D. Therefore, f has both maximum and minimum value. To conclude, the MA1 theorem works for one variable, but in MA2, we often work in Rn, so we need a higher dimensional version. The main idea is still the same. Compact domain plus continuous function means maximum and minimum are attained. This theorem is useful because many optimization problems first need to one basic guarantee. Before we find the biased point, we need to know that the best point exists. That is what the extreme value theorem gives us. Thank you for your listening.